All right, so we have, we're given a graph of a function here, y equals p of x. We're told to assume that every one of these segments is a straight line. So for part A here, we want to talk about any of the points for which the limit does not exist. So what might it look like for the limit of a function not to exist at a point? So one candidate I'll point out is that we have a jump from, at x equals 0 here. And when I say jump, what I mean by this, let's find these one-sided limits. So the limit as x approaches 0 from the left of p of x, well, let's evaluate that. So as we approach 0 from the left, then we are getting a value of 0. What about when we approach 0 from the right? Well, then we are trending towards this value, and that is going to be -2. So the limit as x approaches 0 from the right is -2. So the one-sided limits definitely agree. So what does that mean about the limit as x approaches 0 of p of x? That means that limit fails to exist. So one of our values of a is 0. So now let's look for any others. Do we see any other jump discontinuities like that? Don't see anything else like that, but something else we can look at. Let's at least look at x equals 3. So let's do the same kind of analysis there. What is the limit as x approaches 3 from the left, p of x? As I approach from the left, what value do I approach? Looks like I approach 2. What about when I approach 3 from the right? If I approach from the right, it looks like I also approach 2. So what does that mean for the two-sided limit? The limit as x approaches 3 of p of x. Since the one-sided limits agree, the two-sided limit must share that value. You must agree with those as well. So I believe the only place where we have a limit that doesn't exist is at x equals 0. Moving on to part B. State all the values of a for which p is not continuous at a. So let's unpack that. What does it mean to be continuous? So to have continuity, give you a couple different definitions here. So one of these we can kind of look at as a checklist between 3 different things here. And I'll expand this: continuity at x equals a. So first checkpoint, or first thing to check is this. F of a exists. Is the function defined at x equals a? So that's necessary. What else is necessary? The limit as x approaches a of f of x. That also exists. So to have continuity, we have to have the function being defined at a point, and we have to have the limit of a function at that point also exist. So what's our third condition? Those two things need to agree with each other. So this is like a way to unpack this definition of continuity. But one thing I want to point out is that really all these conditions are wrapped up in this third checkbox here. Because there is no way for this equality to exist if the ideas on either side of the equal sign don't exist. So just a couple different ways to look at this definition. So this is what we're going to look for. So we're looking for a lack of these. So we need all 3 of these things to be true to have continuity. So where are we not going to have this? Well, one point we can say for free is that a equals 0, because we said the limit didn't exist at x equals 0. So if the limit doesn't exist, I can't have continuity. Where else might I not have continuity? So is there anywhere else where the limit fails to exist? Well, that was what we looked at in part A, and we said no. So let's look at the existence of f of a. Are there any other x values on this graph which are not in our domain? And the only other one that I can see is x equals 3. Because what is f of 3? Doesn't look like that thing exists. So I believe we can also say 3. But anywhere else, it looks like, I see solid blue lines at all the other points, or going through all the other points. So I don't think we can say that. I think we can say that every other point is in the domain of this function. And I think we can also say that, if we were to look for limits at those points, they would also be equal to what the function is valued. So I think we have continuity everywhere except for x equals 0, x equals 3. So state all values of a for which p is not differentiable. So another good idea, fundamental idea in calculus to unpack here. What does it mean for a function to be differentiable? So let's unpack this definition again. Differentiability at a. And again, I'm going to give you a couple ideas or a couple different ways to think about this idea. What does it mean for a function to be differentiable at a? Well, one way to think about this is f prime of a exists. Basically, I have a function. I can talk about this, the derivative of that function, and if the derivative exists at a point, it's differentiable. So while that's true, I think we can do a little better. What is f prime of a? So that is something we've talked about, this fundamental limit definition, a lot. So f prime of a equals what? Is the limit as h approaches 0 of f of a plus h minus f of a all over h. So this limit has to exist. So we've also talked about a few ways what would cause this limit to fail to exist. So lots of ways to talk about a derivative, and one thing we keep kind of going back to for graphs is that slope of a tangent line. So the derivative gives you an instantaneous rate of change or a slope of a tangent line. So where am I not going to have differentiability? So we can kind of build up from our last part here. We can say for sure that x equals 0 and x equals 3 are points where this function is not differentiable. Now, why can I say that? Because of this idea. And I'll say this in a couple different ways. If you have a function that's differentiable at a point, then it has to be continuous there as well. So another way to look at that, an equivalent way to look at that is this. If you have a function that's not continuous, it cannot be differentiable at that point. So we already said that our function was not continuous at 0 and 3. So that also means that our function is not differentiable there. If we want to talk about that in terms of the limit, let's look at an example here. What is f prime of 0? Well, that's equal to the limit as h approaches 0 of f of 0 plus h minus f of 0 over h. But this limit right here, we have different behavior on either side of x equals 0, so maybe we should do this. What's the limit as h approaches 0 from the left of this derivative? And the limit as h approaches 0 from the right of this limit, this difference quotient. So f of 0 is what? Is going to be -2. But as I approach from the left, I'm going to be approaching 0. As I approach from the right, I'm going to be approaching -2. So these limits are going to look like what? The limit as h approaches 0 from the left of zero minus -2 over h, and the limit as h approaches 0 from the right of -2 minus -2 over h. So one of these exists and the other one will not. So you already have disagreement. This can't, this derivative is not going to exist. Where else is this derivative not going to exist? Well, if we think about it graphically, anywhere where you cannot draw a unique tangent line. So for example, if we think about a tangent line being a line that only touches a graph at one point, I think I've done it. But here's the thing, I can also do this in lots of other ways. So the derivative that I would characterize there is not unique. I could think about a lot of different ways. So because of that, this function is not going to be differentiable anywhere where I have these cusps, these hard corners. So what are those other x values? I have 3 more x values I have to worry about. And it looks like they are going to be -2, +1, +2. So if we write these in numerical order, -2, 0, 1, 2, 3. And one thing I want to point out here is this is it's not an accident that this list, basically the list I've made for parts A, B, and C here, the list for A is included in the list of B, and the list in B is included in the list in C. Because let's look back at the definitions. First, I was asked for where the limit does not exist. Then I was asked for where it was not continuous. Well, if the limit doesn't exist, I've already failed this middle box for continuity. So if the limit doesn't exist, I can't have continuity. Like I've already lost all hope of having continuity at that point. Similar here, we've said that if your function is not continuous, it cannot be differentiable. So any place where the limit doesn't exist, you have already lost continuity, and so you also lost differentiability. So not a coincidence that we have our list is it includes everything from the earlier list and maybe some more stuff. All right, finally, part D, sketch an accurate graph of y equals p prime of x. So let's do this. Let's make sure we know all the places where this derivative can't exist. So that's x equals, -2, 0, 1, 2, 3. So at those points, those values at x, we can't possibly have derivatives. One thing we're also told that every piece of this graph is a straight line. So how many straight lines are there? I think I have 1, 2, 3, 4, 5. Actually, I'll break that into before and after the discontinuity. So I have 6 different derivatives to find. So let's think about what those derivatives are. These are all straight lines, so I can really find their slopes. I believe the slope of this first one here is -1. So where is that valid for? Looks like everywhere to the left of x equals -2. So I want to have a slope of -1. But one thing I need to be sure about is that, what is the derivative at -1? Sorry, at -2? Well, we've already said that that can't exist. So I need to put an open circle there. So that's the first line segment. What's the next segment? Looks like we have a slope of -1/2. And that continues all the way up to x equals 0. And again, we cannot have a derivative that exists at these endpoints. So we're going to have these open circles. So on the interior, like in the middle of these open circles, the derivative exists, but not at the endpoints. Finally, line segment 3, we have a derivative of 1, and that continues for a single unit. And then line segment 4 here, between x equals 1 and x equals 2, we have a horizontal line. So what's that slope? That slope is 0. And then finally, our last slope here looks pretty steep. It looks like it goes up 1, 2, 3, goes up 3 units and right 1. So I believe that our slope is 3. And it might look like that continues all the way through the end of our graph. But one thing to be careful of is, even though it looks like that's a constant slope, remember where we have, where we fail to have continuity, we also fail to have differentiability. So because of that, I have to put one more open circle at x equals 3. So a lot of open circles in this graph, but as you can see, that needs to mimic all the places where we said the derivative doesn't exist. So that's x equals -2, x equals 0, x equals 1, x equals 2, x equals 3. Okay, so that's the graph for the derivative.